A very good morning and welcome to this course on Foundations of Continuum Mechanics. Today we will be going through the tutorial for week 2, which includes the topics on permutation symbol and the epsilon-delta identity. We'll be doing problems from vector and tensor operations, the use of indicial notation, and contraction and symmetry. We will be solving 6 problems which will help you in your assignment for week 2 and understanding the topic in general. So let's get started. So the first problem, as you can see in the tutorial sheet, which will be available through the NPTEL website, is, so we have to show that the left hand side in this expression is equal to 3 times aijk times xi, xj and xk. So aijk is a third order tensor and xi is basically denoting a vector, and we have to work with the tensorial with indicial notation to prove this. So we will start with the left hand side, and that is typically what we do in problems like this. So the left hand side will be expanded, so we can open the brackets. So this is aijk times xi, xj, xk plus ajki times xi, xj, xk, and the third mathematical term in the expression is ajik xi, xj, xk. So we will number these as 1, 2 and 3 and then deal with them separately. So 1 is good because 1 is 1/3 of what we have to show on the right hand side. So there's a feeling that 2 and 3 have to be shown equal to 1 so that we get 3 times aijk, xi, xj, xk. So let's start with 2. 2 is ajki times xi, xj, xk. So we can see that the indices I, j and k in this term are all repeated indices, that is, they are dummy indices. So they can be replaced with some other index if we want. So we will try to write this in the form of aijk. So what we can see is that a has 3 indices and then we have 3x terms with 3 indices. So the first index of a is the index of the second x, and then the second index of a is the index of the third x, and the third index of a is the index of the first x in this term. So since all these indices are dummy, so they can be replaced with other indices as long as we ensure that the indices with the same color are the same. So what we'll do is we'll make the first index I, so that means that the blue indices have to be I. The second index we'll call j, so the red ones have to be called j, and the yellow one or the orange one has to be called, will be called a k. Now you can see that if we expand the earlier term or this one, they both will expand to the same quantity. So they are exactly the same except that we are using different dummy indices to denote the indices. So let's write it neatly. So this is aijk, xk, xi and xj. So we've been able to get this in the same form as aijk, but the x's are not in the right order. But that doesn't matter because these are simply, I mean, when you expand these, this is xk, xi and xj are simply scalar components. So they can be moved around in any order. It does not change the value of the expression as such. So we can easily write this as aijk. I move the xi first, the xj second and the xk third. So this is exactly equal to what we have in the right hand side here. So we now what we are left with is the third term, which is very similar to the second term. So we will use the same ideas. So term number 3 is ajik times xi, xj, xk. So same idea, we will replace the j with an I. So this x has an index I now, the I with the j, so this becomes a j and the k stays as it is. So we have this k on the last term. Okay, and then we can move around the x's. So this is aijk, xi, xj, xk. So you can see that we have been able to show both 2 and 3. 1 already was what we wanted. So eventually, if we replace 2 and 3 in the expression 1, which was the LHS, so we will say substitute 2 and 3 in the expression 1. So we get LHS is thrice aijk xi xj xk, which is equal to the right hand side. That was to be proved. So this completes the proof. So this is a skill, working with indicial notation, figuring out when to replace the dummy indices with what new indices is a skill that you learn through practice and experience. So this is one of the reasons I suggest that keep practicing problems. Try to think about new problems rather than simply looking at the solutions, and try to solve them yourself, at least for the first time. These kind of methods of replacing the indices are really helpful with simplification in expressions involving indicial notation. So we will be using this skill again and again in this course for simplification of expressions. Right, so let's move on to the next problem. So the second problem says that we have to show that this expression Sij times Aij is equal to 0 if the second order matrix Sij is symmetric and the second order tensor Aij is skew symmetric. So basically what we have to show in the if I write this in the symbolic notation, this is nothing but the vertical double dot between S and A, because Sij Aij, as we showed in the lectures in this week, is simply the vertical double dot of S and A. You don't really need to know this for solving this problem, but I'm just mentioning that because we have seen this in this week. Anyways, so we have to show Sij Aij is equal to 0 if S is a symmetric matrix and A is a skew symmetric matrix. So let's start with the left hand side. So the left hand side is Sij Aij. Now the definition of a symmetric matrix is that Sij is equal to Sji. Right, so this is from the definition of symmetric matrix. And a skew symmetric matrix means that Aij is nothing but negative of Aj. So this is from skew symmetry of A. Right, and now again we use the same idea that both indices I and j in this expression are dummy or repeated. So they can be replaced with any other index as long as I ensure that the same j gets repeated with the same other index. So what I'll do is I'll replace the j with an I and the I with a j. I'll move the negative sign to the left. So this becomes a times I j. And now if I write the if I see the initial and this expression, so what I get is Sij Aij is equal to negative of Sij Aij. So the meaning of a quantity being equal to its negative, it's only possible if the quantity is 0, because if I move the right hand side to the left hand side, what I get here is, in this expression, is twice of Sij Aij is equal to 0. So which basically means that Sij Aij is 0, and this is exactly what we had to show. So this completes the proof. So although I've given you this problem or this relationship as a problem, but we tend to use this as an identity that if you have the product of a symmetric and a skew symmetric tensor, then that is equal to 0. So please remember this, and we will be using this in many problems. So let's go to the third problem. So we have to show using the indicial notation that A cross B dot A is equal to 0. If you had to show using symbolic in this case, that's quite straightforward, because we know that A cross B is a vector which is perpendicular to both A and B. So if you do a dot with an A again, that will be 0. But again, this is an exercise in indicial notation, so I would want you to try it using indicial notation. So let's start with the left hand side. I'll write this expression A cross B dot A using the indicial notation. So this is AI EI crossed with a BJ EJ, and this whole is dotted with an A vector. So we'll write this as AK EK. Again, you have two A's appearing in this mathematical expression, but when you write them in the indicial notation, you have to use different indices for different A's. Right, so let's apply the cross product first. So what I'll do is I'll move the scalar components to the left hand side. So AI and BJ move to the left, and then we have an EI cross EJ, which is nothing but epsilon IJQ times EQ, and this whole is dotted with an AK EK. So now we will apply the dot between EQ and EK. So let's move the epsilon to the extreme left. Then we have the scalar components AI, BJ, AK, and then we have an EQ dot EK, which is delta QK. Now we will apply the substitution property of delta to get rid of it. So I'll replace the index Q with a K in the epsilon. So it becomes epsilon IJK AI BJ AK. Now we will be using the previous problem's result, which said that if you have a product of a symmetric and a skew symmetric tensor, then the result is 0. So in this case, let's take these two as two separate tensors, and we are only interested in the indices I and K. So we'll not worry about the index J. So this epsilon is a tensor which is skew symmetric in I and K. As we saw last time, that epsilon basically is skew symmetric in any two indices because of the definition of epsilon. If you swap any two indices, you end up getting a different order of indices from cyclic to anticyclic, then the sign changes. So this is skew symmetric, and this AIBJAK is symmetric in INK. I am mentioning INK because this expression is symmetric in only INK. If you swap the indices I and k, you get an AK, BJ, AI, which is the same because these are simply just three scalar components, so they can be moved around. The value of this term expression will not change. Now I'm not worried about J. I mean, if you were to expand this as a sum over J, if I am writing, there could be a confusion that we showed this relationship for second order tensors, but these are third order tensors in that we have three free indices in each of these. Well, if you write AI bj ak times epsilon ijk, and this is basically a sum j going from 1 to 3 epsilon ijk ai bj ak. I'm not putting a sum over the other indices as of now. So when you do this, you get basically epsilon I 1k times ai b1 ak. So now we can see that in this, I mean, there will be other terms as well. So each term, if you take it individually, you will see that there will be 0, because in this now b1 can be kept separate, and you can consider ai ak as a second order tensor. The relation that we had, the identity that we had written in the previous problem still holds. Again, I mean, if you're too worried about applying the applicability of the identity, you can in fact show it from the first principles as we did in the previous problem. So you can write epsilon ijk as minus epsilon kji, and you can write the expression aibjak as akbjai, then do a change in indices and then show that LHS is equal to minus LHS, so that becomes LHS is equal to 0. So I will not do that, but if you have any confusion, in fact, I will suggest you try it out yourself as well from first principles, the way we had proven in the previous problem. So if you have a product of a skew symmetric and a symmetric tensor, so that is 0. This is from problem 2. So that completes the proof, where we had to show that A cross B dotted with an A is 0. So we have got a 0 on the right hand side. So let's move on to the next problem. So problem 4 says if Aij, the tensor Aij is given as delta ij times bkk plus 3 times bij, then we have to show two things. First, we have to determine the value of bkk, and second, we have to express bij in terms of aij and aii. So this is a two-part problem where the result from part 1 will be useful in part 2. So let's start with part 1. So in this case, if you look at the expression aij equals delta ej times bkk plus 3 bij. So you have a bij here, but you are asked to determine the value of bkk. So what we'll do here is that we will apply a contraction. Now if you recall, the meaning of contraction is that we set two indices to be the same. So in this case, we have an expression for aij. So I can on both sides apply a contraction. The contraction is I equal to j in the above expression or in the above equation, so that results in AII equals, so I'm just setting j equal to I in this equation, is delta II. BKK remains as it is, there's no change to this index, and then 3 times BII. Now, in case you are having any concerns as to whether we can apply a contraction on this equation or not, let's think about what this equation is. This equation is basically giving us a way to calculate the 9 terms of the tensor A. So A has 9 terms going from A11 to A33. So if I want to calculate A12, all I have to do is, in this expression, I have to substitute I equal to 1 and j equal to 2. So this basically contains a total of 9 equations, one for each component of the second order tensor A. So if this is true for all the 9 components of A, that is, if the LHS of this equation is equal to the RHS of the equation for all 9 components, then I definitely can say that if I sum any 3 components, then this also holds. I mean, if something equal to something, and then I have 3 equations like this, and I add them on both sides, that is also the same. So if you look at AII, that basically is A11 plus A22 plus A33. So all I've done is I've added the diagonals of the tensor Aij if you look at the matrix representation, and I am saying that the sum of the diagonals is also equal to the sum of the corresponding diagonals on the right hand side. So this basically is to tell you that contraction can be done without any issues on both sides, right? So what have we got? Let's simplify this. So we have AII. Now what is delta II? That's delta 11 plus delta 22 plus delta 33. So that's a 3 times BKK plus 3 times BII. Now in this term 3 times BII, I is a repeated index. So I can very well call it a 3 times BKK. Okay. So that's completely allowed because it's just repeated index. And this now, I mean, what is BKK? BKK is basically B11 plus B22 plus B33. So if I'm saying that this is that term which is B11 plus B22 plus C3, this is also the same thing. Okay. So it's better if you represent them using the same index, otherwise it's difficult to see that they are the same things. With time and experience, you will figure out that BKK in an expression is the same as BII. You may not have to do this to this step, but for now let's go slow. So we can easily now add them because they are the same, exactly the same with the same indices. So this is 6 times BKK. So from this we can see that BKK is 1/6 of AII. So this is what we wanted to find out in part 1. Determine BKK. So that's 1/6 of the term AII. So let's move on to the second part of the problem. So in the second part, we have to find the expression for Bij in terms of Aij and Akk. So we can write Bij as Aij minus delta Ij times Bkk, and there's a 1/3 of this. Now we just found out that Bkk was given as 1/6 of AII. Well, actually that's Akk. So we'll substitute that here. So therefore Bij becomes Aij upon 3 minus delta ij upon 3, and there's a bkk which is 1/6 of akk, so that becomes 1/18 of delta ej times akk. So therefore we have expressed bij in terms of aij and akk. So that completes the solution. So let's move on to the next problem now. In this fifth problem, we have to show that the expression epsilon mkq times epsilon jkq is twice of delta mj. So this time on the left hand side we have a product of epsilons. So we can apply the epsilon delta identity as long as the last index of each epsilon is the same, which indeed it is because it's q in both epsilons. So we can apply the epsilon delta identity, which says this product is equal to delta first times delta second minus delta second times delta first. Okay, so delta kk is a 3, so this becomes 3 times delta mj, and then you have a common index in these two deltas, so any of these can be substituted. So I'll substitute the second delta here, so this becomes delta m times j. So I've applied the substitution property in this second term. So this is 3 times delta mj minus delta mj, so that is equal to 2 times delta mj, which is equal to the right hand side as we can see here. So this completes the proof. So now we'll move on to the last problem of today's tutorial, that is problem 6. So we have been given a tensor equation. Sigma ij is lambda times delta ij times epsilon kk plus twice mu epsilon ij. So it's again a two-part problem. So in the first part, it is asked that how many scalar equations does this tensor equation represent, and in the second part it says how many terms are there on the right hand side of each equation. So this problem is being provided for you to appreciate that the use of indicial notation results in a large amount of compaction of the information. So let's solve this problem. So if you look at the equation for sigma, so sigma has two indices I and j, where I goes from 1 to 3 and the index j goes from 1 to 3. That is, they take the values 1, 2 and 3 independently. So we have a total of 9 scalar equations in the tensor equation that's provided to us, because there's an equation for sigma 1 1. If you substitute I equal to 1 and j equal to 1, there's an equation for sigma 1 2 all the way to equation for sigma 3 3. So we have a total of 9 equations. One for each component of sigma ij. And then in the second part, it is asked that how many terms on the right hand side of each equation. So this is the equation, and we've been asked that how many terms are there on the right hand side of each equation. So let's expand the right hand side. On the right hand side has and epsilon kk. So that epsilon kk expands to epsilon 11 plus epsilon 22 plus epsilon 33. Now this equation is, we have 9 equations where each equation is for a given component of sigma. So each equation will have distinct values for I and j. So I'll not touch that. So I and j, so these terms stay as it is, and I and j can be substituted. So this, we'll expand this. So this becomes lambda epsilon 11 times delta ej plus lambda epsilon 22 times delta ej plus lambda epsilon 33 times delta ej. So we have a total of 4 terms on the right hand side for each sigma I j. So what we have seen is that we were able to very compactly write the nine equations, each having 4 terms on the right hand side, by simply this expression. So this is another reason why we tend to use the indicial notation, because this greatly simplifies the expression, and the amount of information that can be compacted into a small equation is very useful. So we will stop here. That brings us to the end of this week's tutorial, and I'll see you next week. Thank you.